Okay, last talk is multi-objective optimization. Like most talks, again, there's usually a chapter, or at least a section in your book about these ideas. So we had Nelder-Mead was a nonlinear optimization, NMF was a nonlinear optimization. We did the alternating least squares thing. Evolution optimization. I'm not sure if there's a chapter in Ryder on that. There's definitely chapters in Ryder on nonlinear optimization. And then we're about to do a multi-objective optimization. And there's definitely chapters on that, on multi-objective optimization. And you've seen a little bit in, was it chapter 1 and 2 when you were learning vocabulary? Okay, so this is a former student that did a thesis here and then went on to do a PhD in operations. This problem when Tim Chartier at Davidson had some data on assignment problem. And so we'll talk a little bit about assignment problems, whole chapter on assignment problems. Great use of OR. Folks often get hired to solve assignment problems for airlines, for Amazon. So here's a picture of one. Maybe you got 4 machines and 4 operators. And you're trying to, it makes this graph, every machine could be run by a different operator, and you're trying to make a schedule where which operator is running which machine. And so every machine must be covered, every operator must be assigned to a machine, one and only one machine. So there's some constraints, and you can see that it's really just an integer program, right? So Xij, machine I is assigned to be run by operator J. The sum of the i's has to be, the sum of Xij over all the i's has to be 1. Every machine has got an operator and every operator has a machine. Assignment problem workers to jobs. Again, you think about it as a matrix even. There could be weights for this assignment of worker 1 to job A. Maybe that's a preference that they prefer it. They'd rather do job A than they would say job C. And you might want to then do the assignment, but maximize worker preferences. You can also think about it again as a graph. Here's all the different ways you can make these assignments. Here's the optimal assignment. It's just out of all the links that exist, these dark ones are chosen. Another common one is machines to jobs, like in a plant, a factory. This is an assignment where like machine 1 goes to job 5. So again, you can see every row has a sums to 1, every column sums to 1. And then again, maybe there's some objective beyond just satisfying constraints, you have some objective. Okay, the easiest case is when the number of items over here is equal to the number of items over there. If that's the case, then you can do something called the Hungarian algorithm, which is very efficient and solves that easy problem. But most assignment problems have a little bit more happening. Either there's an unequal number, like maybe there's 4 machines and 10 jobs or something. Well, here's the Davidson College student volunteer assignment problem. Davidson College, they have a program where the students there have to volunteer, and they fill out a form. And the woman that actually ran the office there used to try to do this by hand, and she asked my colleague Tim Chartier for help, and then he asked me for help because he didn't know as much optimization. He's an applied mathematician, but not an OR person. So we worked on it, and Tori ended up making this part of her thesis. So she solved this specialized assignment problem, which is a very hard case. What they had was students needed to be grouped, and every group needed to have a student that had a car or was could drive, borrow a car, drive one. This is before Uber. And yeah, so again, every group had to have more than one vehicle. They wanted the groups to be diverse, so that's these different colored things. Students had partner preferences, so like this student and this student would prefer to work together, this one and this one. They also had availability preferences on the times that they could make it to the local, these were local middle schools, I think, that Davidson College students went and visited local middle schools and volunteered there. So it had to meet availability preferences. You'd like it to meet partner preferences. You'd like the groups to be diverse. These are some of the things that the Davidson office said. There was, again, a woman that used to have to do this by hand. She would just collect the information. They had a little survey that every student filled out with, like, when they were available, did they have a car, who would they like to work with, gender or race, and then they needed to make these assignments. And there was an equal number of students to classes, and there might be some unassigned students that just, they were only available at, like, Monday morning at 8, and they couldn't make it to a class or something. So they're also unassigned classes. So this was the form that they got, the Davidson officer got. She said this was a nightmare for her, just ruined like weeks of her life, and she would try to do it by hand in these paper forms. She would sit in her house and lay out all these paper forms on the floor and try to like visually do some sort of organization. Definitely not optimal. And so Tori was able to come in and give an optimal solution, make the code, and they could just hit it every year, enter this data to, I think they ended up entering to a website, which then fed it to a database, which fed it to Express, was the production code that we were using at the time. We were able to get like a student license or something at a discount. Okay, so they collected this kind of information. When are you available to go to that middle school? Availability versus preference. Like, okay, I'm available at 8 in the morning, but I'd rather not have to wake up that early. So 10 is what I'd prefer. Do you have a vehicle? Do you have a partner preference? Gender and race. Okay, so now we're going to get to this as a multi-objective optimization. So the Davidson officer said this is the things they'd like to maximize in order of most to least important. So like number one, they wanted to see how many Davidson students they could put in the program and have volunteer. Number two, they'd like to make the Davidson students happy, so they were participating at their preferred times. Number three, it'd be great if they could get their preferred partner. And number four, it'd be really great if the middle school saw that Davidson was more diverse than maybe they thought. They don't want to send 4 white males if there's a way to make group diverse. All right, so we had many objectives to meet and many constraints. Maybe we won't go into, maybe just this. So often multi-objective work is handled as a single objective. So these objectives, you just lump them with weights. So you say like objective function F1, number of student who can participate, and you give that a weight. So Tori could go back to the Davidson program officer and say, you ordered them, but could you be more specific? Could you give them each a value between 0 and 1, and so that they all sum to 1? So you should have like percentage weights, like how important is that? 70% important to you, and then this one's maybe 20% and 10%, and so on. So you could get those. If you did that, then you just lump them all together into one objective. This is not ideal, but this is a way to handle a multi-objective. It's probably the most common way that folks handle multi-objective work, is they just lump it into a single objective. I think I won't do the stable matching. Cool stuff. Stable matching is really cool, but we'll just stick with the multi-objective. So Tori's idea was to do this as what's called a sequential multi-objective. So you often see MOO, so sequential MOO. So we would try to optimize this first. So we'd run the problem with just this objective. We get a value. Maybe it said the optimal number of students who could participate. We maximized it, and there's 100 who can participate. So then she would take that and make it a constraint for the next F2. She'd say, okay, now I want to maximize the number of students who can participate at their preferred times, given that 100 of them have to participate. And then the phase 3, she would say, make the first 2 phases constraints. So maybe then preferred student times was less than that, like only 90 of them. So she'd add that as a constraint. So we have 2 constraints that got added to the phase 3 and down to the phase 4. So some input variables. If the student was available, this was just a binary 0 or 1. This is data. Maybe variables not the right word. These are just input data. 0 or 1 if they had a vehicle, and if the teacher requested class C. Then the things that she was actually deciding was assigning a student to a class. So student S to class C. And then if class C actually got a group assigned to it, because remember, there could be some unassigned middle school classes. She needed that to, I think, do the diversity constraint. Okay, so we're gonna, again, do these sequentially, these 4 objectives. This is a much better approach than the weighted one, but there's even better beyond that, which another student of ours, a master's student, went on and got his PhD in optimization and OR at Georgia Tech. He just did his defense actually last week. And he did a multi-objective algorithms that don't do it sequentially. They actually handle it simultaneously. It's much more expensive, but it's preferred. It's the optimal way to do it. Okay, so weighted, then sequential, and then simultaneous. So Tori did sequential here. Much more tractable to do, right? They go in order of tractability, but also in order of, what was our other word? Validity. Okay, so phase 1, she's maximizing the number of students can participate. That was the availability scalar input data. So maximize over the X. And then there's all these constraints. Those are the things that we just said in English. It's nice to write next to each one what it means. Like here's the vehicle per group. If the class was used, they definitely needed to have a vehicle among the students. Each student had to be assigned at most 1 class. So a student could be unassigned or 1 class. They couldn't be going to 2 or 3 volunteer opportunities. They had to meet their availability. They wanted, if the teacher asked for like multiple middle school classes to be covered, they said, well, maybe we can't cover all of them, but we'll at least meet one of them. And then the decision variables were all binary. So in terms of running this in, say, MATLAB, kind of a nightmare to generate the A matrices for it, but you'd be doing int, lin, prod. We didn't have to do that in MATLAB. We were able to do it in Express, where you can kind of write it in a much more similar syntax to what we see here. Okay, phase 2. Now we're maximizing a different objective, but we're keeping those 7 constraints here, and we're adding the phase 1 objective. So again, if 100 students could volunteer in the program, that's what we want to happen. And then we want to say, of those 100, how many get their preferred time? And so maybe that came out to be 90. In phase 3, we actually need to add more variables. So we actually need a triply indexed variable, y, also binary. So the whole thing all the variables ended up being binary integer linear programs, which happens often. You saw that this semester with Shikoku. And again, original constraints say, and then you keep adding for each previous phase, you add a constraint that makes sure that objective value is met. And then here we're trying to make sure that the groups get their partner preferences. And so she makes this the objective, and then we added this constraint to do that. This one was tricky. It took us a while to figure that one out, if I remember right. And then last one, diversity. So all the previous constraints plus those previous objectives, and then a similar constraint, similar objective to meet diversity. And then what she did, so she had some data from that year, but that was the only one that had years, and they've been collecting since and keeping it. So she made up a lot of artificial examples to test her model. She said, okay, what if there's 46 students, there's 19 middle school classes, groups are size 3 to 5. So she made a small, medium, what she called large, and extra large problem if there were 500 students, beyond what Davidson usually gets in the folks that are doing the volunteer program, but just to see what happened and see where it broke. And you can see in some cases that at phase 1 and 2 are okay, but phase 3 is where it runs out of memory. But why that happened? Those were the triply indexed variables. So we had an S1 times an S2 times so like a number of students times a number of students times a number of classes, I think it was. So it can easily get really, really big. And she just did some run times. Okay, so that's MOO, multi-objective optimization, done in a sequential manner. Some key points on that is the weighted objective function for a multi-objective is sort of the trivial thing you should try first. that's not the best. Then usually there's a sequential approach. And then beyond that, there's a simultaneous, which is much more advanced, more valid, but less tractable.